So this video is intended to follow the video on the epsilon-delta definition of the limit of a function. In this video we're going to have a look at the definitions of one-sided limits of functions. So these are things that I'm sure you've seen before in calculus, expressions like this and this. So here we have the right-hand limit of the function f of x as x approaches a, and here we have the left-hand limit of the function f of x as x approaches a. And we denote this by saying x approaches a, and then if you see the plus symbol there, that means from the right-hand side, i.e. from the numbers that are bigger than a. And if you see the negative symbol there, that means from the left-hand side, so the numbers that are smaller than a. Now, in the cases where the full limit exists and is equal to some value L, then both of these things will exist and they will both equal one another. However, in other cases, it might be the case that both of these independently exist but are not equal to one another, and in that case the overall limit will not exist, and for that reason I have written this one as L and this one as L bar, because in general the right-hand limit and the left-hand limit might not be the same. So I'd like to show you an example of where the right-hand limit and the left-hand limit both exist but are not equal to one another. And for this, we're going to take an example, and we're going to use this example. So this is quite a famous function. We're letting f of x equal what's called the sine function. And this is not the sinusoidal function, the sin function. This is the sgn function. And it's short for sine, spelt S-I-G-N. And it is the function that takes all the positive numbers and maps them onto 1. So we have our axes here, so we're plotting f of x on the vertical axis and the domain is on the horizontal axis as usual. And in red here is the function plotted. So for all the positive real numbers, it's going to map them onto 1, so they're all being mapped onto 1 here. For 0, it's mapping it onto 0, and then for the negative numbers, it's going to map them onto -1. So really, it maps each number onto its sign, positive or negative. So all the positive numbers are being mapped onto 1, and all the negative numbers are being mapped onto -1, and then 0, which is neither positive nor negative, is being mapped onto just 0 in the middle there. So that is the sine function, or an even fancier name you might see used for it is the signum function. So hopefully you don't need me to tell you what point in the domain is going to be the interesting point to look at the limit of this function. It is, of course, the value 0. Now, if we look at what the value of the function actually is at 0, by definition, it's 0. So sine at 0 is 0. But now let's ask the fancier analysis question, what is the limit as x approaches 0 of our function sine of x? So there are 3 natural candidates. Maybe it could be 1, maybe it could be 0, maybe it could be -1. Let's start off with the one in the middle. That seems like the best of the 3 candidates. So could the limit of this function be 0? Well, the answer is no, because remember what it means for the limit to be 0. It means that it gets and stays indefinitely close to 0 as you get closer and closer to 0 in the domain. Now, as you get closer and closer to 0 in the domain from both sides, you are not getting indefinitely close to 0. So we really need it to get indefinitely and stay indefinitely close, but it doesn't even get indefinitely close because all of these values up here on the positive side are 1, and all of these values on the negative side are -1. They never get any closer than that, so the difference between the value of the function and this value 0, which we're proposing to be the limit, is always going to be size 1. It's never going to get smaller than that. So the function isn't going to get indefinitely close to 0 as x approaches 0. So we can rule 0 out as a candidate. I've put a cross through that one. Let's now look at the other 2 candidates. Let's look at 1. Could 1 be the limit as x approaches 0 of sine of x? So in this case, it does get indefinitely close to 1, because if you look at us tailing in from the positive side, the value of the function is always equal to 1 for these positive numbers, which is distant 0 from 1. So it is indefinitely close to the limit. However, it does not stay indefinitely close, because if you then look at the other side, which is of course important when we consider the overall limit, it's always equal to -1 on that side. So if, for example, I consider the epsilon interval around 1 of radius 1/2, so this is the interval 1/2 to 3/2, if it were the case that the limit of this function was equal to 1, then I should be able to find you a delta interval around 0, so an interval negative delta to delta, where all of the points inside that interval, excluding the centerpiece itself 0, are mapped into that half interval around 1. Now, of course, that's not going to work because for all delta greater than 0, this interval is going to contain some of these negative numbers here that are going to be mapped onto negative 1, which is, of course, going to be outside of this interval. So therefore, the limit of this function as x approaches 0 cannot equal 1 because the function doesn't even get and stay within a half distance of 1, never mind get and stay indefinitely close to 1. So we can cross 1 off the list here, and of course negative 1 is going to fail as well for the exact same reason as 1 fails. So again, the function does not get and stay indefinitely close to negative 1. It does get indefinitely close to negative 1 because of course it's negative 1, negative 1, negative 1, negative 1 for all these negative numbers, so it's distance 0 from our proposed limit for all of them. But the problem is for all of these positive numbers it's equal to 1, 1, 1, 1, 1, 1, which is not staying indefinitely close to negative 1. So again, we can consider an epsilon interval of radius a half, so the interval negative a half to negative 3/2 that is centered around negative 1, and I cannot find you a delta interval around 0, an interval from negative delta to delta, where delta is greater than 0, such that all the points inside that interval, bar the centerpiece itself 0, is mapped into this interval, because of course for those positive numbers that are included in that delta interval, they're being mapped onto 1, which is going to be outside of this interval. So again, I can conclude that this function does not even get within a half distance of negative 1 and stay within that distance as x goes to 0. So it certainly can't get and stay indefinitely close to negative 1. So minus 1 crossed off, that's the last of our 3 natural contenders for what the limit of this function is equal to. Now you might wonder, could some other real number be the limit of this function as x approaches 0? Well, it's quite easy to see that that's not the case. If we considered that possibility, let's say this real number up here, L, is our possible limit of this function, we can quite easily disprove that because the value of the function has only 3 possibilities. It's either equal to 1, or it's equal to 0, or it's equal to negative 1. L we're now assuming is none of those 3, it's some other real number. So we can then look at what the distance of L from these 3 numbers is. So we can look at the distance from L to 1, we can look at the distance from L to 0, we can look at the distance from L to negative 1. Now, one of those 3 distances will be the minimum. So in the case of this picture where we've put L up here, it would be the distance from L to 1 would be the minimum. It would be this distance here, and that's L minus 1. That then is the closest the function can ever be to this value L, because it's the minimum of those 3 distances. Therefore, the function cannot even get indefinitely close to this proposed limit L. Never mind get and stay indefinitely close to that limit L. So that's the reason we can rule out any other real number being the potential limit of this function. So once these 3 natural contenders are gone, we can therefore say overall this function doesn't have a limit, hence why I've put a cross through it. So even though this function doesn't have an overall limit as x approaches 0, it does have a right-hand limit as x approaches 0 and a left-hand limit as x approaches 0. So the right-hand limit of the function as x approaches 0 is equal to 1, and the left-hand limit of the function as x approaches 0 is equal to negative 1. So hopefully this is reasonably intuitive to you, but looking at the picture, if we think about now just coming in from the right-hand side, the function does get and stay indefinitely close to something, and that number is 1. If we think about just coming in from the left-hand side, again, the function does get and stay indefinitely close to something, and that is negative 1. So it gets rid of this problem of it jumping from negative 1 to 1 as you go across 0. So let's turn this into a general formal definition then. So we're now approaching a general point A rather than the point 0. So the limit as x approaches A from the right-hand side of a function f of x equaling some value L, the meaning of this is that for all epsilon greater than 0, again there must exist a delta greater than 0 such that if x is an element, and now this is the bit that changes, previously it was of the interval a minus delta to a plus delta excluding the centerpiece a. We've now got rid of the left hand side of that interval and we're just taking the right hand side, and because we're making it an open interval, this also helps us get rid of that centerpiece a. We don't have to have that awkward subtract a at the end now. So if x is an element of the interval from a to a plus delta, so that's just the right-hand side of the interval to the right of that centerpiece a, but not including that centerpiece a, it's the open interval, then if we look at the value of f of x for all of those things inside that interval, it must be within the epsilon interval. So you must be able to find a right-hand interval on the right-hand side of A such that it's mapped entirely into the epsilon interval around the limit L. So we'll understand this with a picture here. So here is our vertical axis and here is our horizontal axis, domain on the horizontal axis, codomain on the vertical axis, and we've now got the graph of our function here, and here is the point we're approaching A, and this now shows a more general problem where the right-hand limit is not going to equal the left-hand limit. So from the right, the limit is going to be this value here, L, and then from the left, the limit is going to be this value here, which I've called L bar, and the value of the function at A is actually equal to L bar, hence why I've drawn a solid dot there, and then this hole here. So intuitively, what we want to capture is that as you come into A from the right-hand side, the value of the function gets and stays indefinitely close to this value that we are calling the right-hand limit. The reason then that this captures this is that it's saying however close you want, I can build you this little epsilon interval around this thing that we are proposing as the limit. So this interval L minus epsilon to L plus epsilon, and I must be able to find for every one of those closenesses, epsilons, you must be able to find an interval to the right of A, this interval A to A plus delta. There must exist a delta that is greater than 0 such that this entire interval is mapped within that closeness of L. That is therefore capturing the fact that it gets indefinitely close, but also the fact that it stays because it's the entire interval. So everything from here all the tail way into A, indefinitely close to A, but not actually including A, all of them are going to be that close. So it's not just capturing that it gets indefinitely close, it also captures that it needs to stay that close. Going back to this example up here, I just want to convince you that this satisfies this definition for having a right-hand limit equal to 1. So I need to be able to show you then, for whatever epsilon, that I can find such an interval to the right of 0 that is mapped inside of that epsilon interval. So if I have the interval 1 minus epsilon to 1 plus epsilon, I now need to find an interval from 0 to delta such that it's mapped entirely into that for each one of the epsilons. Well, this is simple. I can actually use the same delta for all the epsilons. If I make delta equal to 1, consider this interval from 0 to 1, all of those numbers are going to be mapped onto 1, which is distance 0 from 1, so they're certainly inside of this interval. They're always inside this interval, no matter what epsilon, because 1 is always the centerpiece of that interval. So truly, I've shown you then that I can find a delta for whatever epsilon you give me that is going to be mapped entirely into that epsilon interval. So this does satisfy this definition for the right-hand limit equaling 1. So now let's have a look at the definition for the left-hand limit. So this is very simple, so hopefully it should occur to you what changes are necessary to be made to this definition for the right-hand limit to turn it into the definition for the left-hand limit. But here it is. So the limit as x approaches a from the left-hand side of f of x is equal to L bar. The meaning of this is that for all epsilon greater than 0, so however close you want to be, there must exist a delta greater than 0 such that if you look at the delta interval to the left of a, so the interval a minus delta to a, then all of the points in that interval are mapped into the epsilon interval around L bar. So f of x is an element of L bar minus epsilon to L bar plus epsilon. So again, what this is saying on the picture is however close you want to be to your proposed limit L bar, then you can consider that closeness interval around L bar, so this epsilon interval around L bar, so from L bar minus epsilon to L bar plus epsilon, and it must be possible to find a interval to the left of A, so this interval A minus delta to A, but not including A, such that all of those points are mapped into that closeness around L bar. So that captures the fact that it gets indefinitely close because it must be true for all epsilon, for all closenesses greater than 0, and also the fact that it stays because everything in this interval all the way tailing into A is mapped into that closeness. So the next important point is that if the overall limit of the function as x approaches a exists and is equal to L, then that implies that both the right-hand and the left-hand limit of the function will exist, and they will be equal to each other, and they will both equal L also. So that's this arrow of our biconditional here. The other way round holds true as well. If both the right-hand limit and the left-hand limit of the function as x approaches a exist, and they are both equal to one another, equal to L, then that implies that the overall limit of the function as x approaches a exists and is equal to L. So there is a biconditional relationship here. So let's understand why this is true, and we'll start with the forward direction. So we'll start with the assumption then that the overall limit exists, so the limit as x approaches a of f of x is equal to L, and we want to derive that the right-hand and left-hand limit exist and are equal to L. So we're going to use this picture to help us understand. So again, we have the domain on the horizontal axis, the codomain on the vertical axis. This graph is then representing our function f of x, and we have our point that we're approaching in the domain here is a, and then the limit as x approaches a of f of x is equal to L, and that's marked on here. Now in the case of this picture, the value of the function at a is actually equal to the limit as x approaches a of the function is equal to L. However, for this theorem to be true, that wasn't necessary. So I could have had f of a being something, for instance, down here, something totally different, and then I'd have had to draw a hole here where the limit of the function is. However, for the sake of a pretty picture, I've drawn it without the point discontinuity. So from the fact that this is true, I know that for all epsilon intervals around L, so the interval L minus epsilon to L plus epsilon, I can find a delta interval around A, so the interval A minus delta to A plus delta, such that all the points inside that interval, bar the centerpiece itself A, will be mapped into the epsilon interval around L. Now please don't get confused by the picture, because in the case of the picture, A of course is going to be mapped into the epsilon intervals around L, because f of A on the picture is equal to L. But that isn't part of our starting assumptions. I just did that for a pretty picture. I could have had f of a being something down here, for instance. So just from our starting assumption, which is this is what I can get, that I can find you a delta interval such that all the points in it, bar the centerpiece, are mapped into here. To conclude that a is mapped into here, I would have had to have another starting assumption, which is that f of a is equal to L, but we're not starting with that assumption. That's just for the sake of a pretty picture, but I could have drawn this picture more generally as having f of a something totally different, so please don't get confused by that. So let's now show these two things, and we'll start with the right-hand limit. So in order to show this, we need to show that for all epsilon, we can find the right-hand interval to the right of A such that all of those points inside that interval are mapped into the epsilon interval around L. So hopefully it's immediately obvious to you how to do this from this starting assumption. So from this starting assumption, it's the case that for all epsilon intervals around L, you can find an interval A minus delta to A plus delta such that all the points inside it are mapped into that epsilon interval. So just now take the right-hand side of this interval, take the interval from A to A plus delta, which is a subset of this that is being mapped into that epsilon interval, and that's the interval that you can use to satisfy this definition. Similarly, for this left-hand limit, you just take the left-hand side of this interval, the part of it from A minus delta to A, and we know that that will be mapped into this epsilon interval around L. And because you can construct one of these intervals for all epsilon, you can therefore construct these intervals for all epsilon also. So let's now do the other way round. So we want to start with the assumption that these two things exist and are equal to one another, and we want to derive that the overall limit exists and is equal to this value L. So to show this, we need to be able to show that for all epsilon intervals around L, we can find a delta interval around A such that all the points inside it except the centerpiece are going to be mapped into that epsilon interval around L. From these two things being true, starting with this one being true, we know that for this epsilon interval, we can find a delta interval that is to the right of A, so an interval A to A plus delta that is going to be mapped entirely into that epsilon interval. Then from this one being true, we know that we can find an interval to the left of A, an interval A minus delta bar to A, such that all of those points inside there are going to be mapped into the epsilon interval around L. Now delta and delta bar might not necessarily equal one another, but we can sort that out easily. So on the picture, in orange here, this is the interval from A to A plus delta, and in red, this is representing the interval from A minus delta to A. So we know that all the points inside the orange interval are mapped into this epsilon interval around L, and all the points in that red interval are mapped into this interval around L. What we now need to do is find an overall interval that's centered around A such that all of its points, bar the centerpiece, are mapped into that interval around L. So quite simply, all we need to do is look at which one of delta and delta bar is the smaller and use that as our overall delta for our interval centered around A. So on the picture, quite clearly it's the orange one that is smaller, so we'd use delta. More generally, let's call delta prime the minimum of delta and delta bar, and then we'll take the interval A minus delta prime to A plus delta prime. And now my claim is that all the points inside of there, apart from the centerpiece A itself, are going to be mapped into the epsilon interval around L. And the reason you can see that is you can split this in two. So we have the interval A minus delta prime to A and the interval A to A plus delta prime, and all that's got rid of is the centerpiece, which we don't care about anyway. And we know that this is going to be contained inside this, and this one is going to be contained inside this one because delta prime was the minimum of these two, so it was less than or equal to both of them. So that is how you can find a delta interval that is mapped into the epsilon interval around L for any epsilon from the fact that these two limits exist. So overall, we have shown that if the right-hand limit and the left-hand limit of a function exist and they are equal to one another, then you can conclude that the overall limit exists and is equal to whatever the value of those right and left-hand limits were. So the final thing I'd like to talk about is the fact that the sequence characterization for the limit of a function is going to carry over into the case of these one-sided limits. So we'll discuss this for right-hand limits, although the exact same thing holds true for left-hand limits. So if the right-hand limit of the function f of x as x approaches a is equal to L, then an equivalent characterization of this is that any sequence that converges to A where the terms of the sequence are greater than A will have its image sequence converging to L. So on the picture, here is our domain, our codomain. We're approaching this value A from the right, and it's approaching some value L. So what we are saying is if you take any sequence of real numbers that converges into A, where the terms of the sequence are not allowed to equal A, and they're all on the right of A, so they're all greater than A, but they're converging to A, then the corresponding image sequence, f of xn, will converge to L. So from this, you can conclude this. Equally, the other way round holds true, just as it did for overall limits of functions, that if it's the case that all such sequences that the terms are greater than A, that converge to A, have an image sequence that converges to L, then you can conclude that the limit of the function as you approach A from the right-hand side is equal to L. So I'm only going to briefly talk about why this is true, because the proof of this follows the exact same strategy as we took for proving this in the case of overall limits in the video on the epsilon-delta definition of the limit of a function. So a few words then on the forward direction. So we're starting with the fact that the right-hand limit is equal to L, so that means that the value of the function gets and stays indefinitely close to L as you come into A from the right-hand side. This sequence is coming into A from the right-hand side, so then it follows that its image sequence is going to get and stay indefinitely close to L and converge to L. That's the basic idea of why this is true. The backwards direction would be a proof by contradiction, just like we did in the video on the epsilon-delta definition. So if this were not true, we would be able to construct a sequence that converges to A from the right-hand side, so where all the terms are greater than A, such that its image sequence does not converge to L, and that would contradict our initial assumption that all such sequences that converge to A from the right-hand side, i.e. the terms are all greater than A, must have image sequences that converge to L. So the sequence characterization for the limit of a function carries over into these one-sided limits in the form of these sequences that converge to A from one side. So in the case of the right-hand limit, you're looking at sequences that come in from the right-hand side where all the terms of the sequences are greater than A. In the case of the left-hand limit, you'll be looking at sequences that come into A from the left-hand side, i.e. you'd need to change this to all the terms of the sequence need to be less than A. Final thing to say is that because the sequence characterization carries over, the algebra of limit results then also carry over for one-sided limits, and the arguments are exactly the same as what we did in the video on the epsilon-delta definition. So we'll end this video here. Thank you for watching.